Now, how can a particle of the size which produced all our matter be so escaped? It eludes science just because no one in their right mind can get their hands on it. Scientists reveal a strange discovery at the Large Hadron Collider, and we realize we got the God particle all wrong. Higgs boson was supposed to be our key to the creation blueprint, but what we've got is the door to another hidden dimension of reality we never knew existed. At the magic threshold, the smallest particles which make up our world have the potential to gain mass at this threshold. What was pure possibility, pure energy, is now visible. The energy field that governs the universe, proposed by the physicist Peter Higgs as early as 1964, is this one. This field is made up of a particle, the Higgs boson. A researcher nicknames the particle God, or the God particle. For more than a decade, particle physicists have been searching in vain for Higgs bosons in today's famous Large Hadron Collider. Today, many questions still remain about the behavior of these tiny units of our creation. But why do these bosons behave so out of control? So, after appearance, why do they split into many other particles and become almost impossible to study? Explaining. The Higgs field as an ocean of invisible stuff is something researchers like to do. This field comes into contact with every single elementary particle known, but each reaction is different from the next. The Higgs field is like a big, elegant fish tank. Photons, or particles of light in other words, swim through the Higgs field like sleek, streamlined fish. They go through because if they touch the field can react pretty much only with beautiful stretches. Like a smooth fish in water doesn't create any waves or resistance. But particles such as electrons or quarks don't have quite so elegant a relationship with Higgs field. It's like they tend to behave as an average human swimmer. We're also very graceful in the water, but we generate a bigger overall resistance. And a lot more waves. W and Z bosons behave as a smooth ball would float either on or in water. It isn't quite touching the ball in a way where it starts to interact with the water actively, but neither does it make a lot of water ripple. Finally, it's the really fun thing about this field, the Higgs boson. There are waves on its surface, it floats. This Higgs boson is the key for scientists to understand mass conferral. Not only is this a part of the field, it is the official appearance or proof of its existence. It was first discovered at the Large Hadron Collider of the CERN organization in Geneva, Switzerland, in 2012. Higgs' theory from the 1960s had been proved. With its help, we should be able to ascertain how the matter is made. The Higgs boson is so very heavy compared to other particles. It weighs approximately 125 giga-electronvolts per the square of speed of light, about 133 times more than a proton. The reason the Higgs boson was so revolutionary a discovery is that it proved that the Higgs field, which had long been theorized, is real. As more particles interact with this field, then more mass the particles are given, and if it follows, there is then more weight. The counterintuitive thing is that photons, the elementary particle version of carriers of light, don't interact with the Higgs field at all, but they slip through and they are massless and, of course, incredibly fast. Is matter really volatile? But what is often overlooked is that these particles, Higgs bosons, are actually the basic fabric of our matter, and they are unpredictable. With their short lives, scientists describe Higgs bosons as unpredictable. However, Higgs bosons live only about 10 to the power of 22 seconds, and during that time only decay into other particles. To these decay processes, scientists also can get quite a bit of new information about the properties of the Higgs boson. But this particle does not make it any easier for scientists. This decays in such a confusingly and unpredictably way that there is almost nothing that can be concluded from it. For now, it seems like we are going further and further away from finding out what the Higgs boson's key role in the universe is. We still just know that somehow they are somehow making these other elementary particles all have mass. We don't really know what they themselves are because they are so fleeting. It's hard to even imagine. Of course, the Higgs boson, and specifically the Higgs field, are also certain to be essential for the world as we know it then. Without the field, there would be no atoms, no molecules, no elements, no trees, no birds. In fact, had it not been for Higgs bosons giving electrons, protons, and neutrons their mass, our entire globe really only exists. In fractions of a second, it decays in something of subatomic range. In the subatomic world, such decay has so far yielded observation of directly produced W and Z bosons, which are carriers of the weak nuclear force. But there is also decay to more massive relatives of electrons, tau leptons. It's particularly exciting because decay of the Higgs boson into photons is one of areas where we believe we've made significant progress. This tooling is driven through the work of a complex mechanism which is called a loop, and wherein virtual particles are appearing and disappearing. The decay into a photon and a Z boson is puzzling even more. A recent study at the Large Hadron Collider has found that this decay occurs almost 6.5% of the time, when standard model calculations predicted a rate of 0.15% or less. But the scientists haven't been able to create a rule, and it almost feels like the Higgs boson is acting increasingly insane as researchers inch closer. Still, with each and every one of their test runs, the scientists know that they are turning open windows onto previously undiscovered particles and phenomena. One day, these studies will be the keys in understanding nature and the universe. The standard model of particle physics is first of all crisply admitted to be the starting point from which everything has to be incorporated into, first of all, these surprising new observations. The fact that the deviations from theoretical predictions may indicate new aspects of the subatomic world is a first hint of previously undiscovered aspects and forces in the subatomic world. That is, they could also transform the way we understand matter and energy. The newest model of particle. Physics is also no longer the standard model of the basic forces. Developed in the 1970s, it was a theoretical framework that describes the fundamental particles and forces that make up our universe. Quarks and leptons are among the particles, photon and gluons are among the force transmitters, or perhaps the Higgs boson. Until the work in Geneva, these were long, pure assumptions. The discovery of the Higgs boson, celebrated in 2012, it was said, completed the picture with the last missing piece of the puzzle in this model. The Higgs boson is unique because with a mass around 125 giga-electron-volts, it changes. It is also unusual for opting for the Higgs field as a way to impede other particles in developing mass. If we can't so much as describe a particle whose very location is integral to modern physics with the rules at our disposal, how can we possibly say that a particle like that will be the final piece of the puzzle? This discrepancy is of considerable importance. And so, the standard model has fared extremely well in countless experiments, with predictions that are accurate to within fractions of a percent. It only fails when there is the Higgs boson. Alternately, we may be dealing with a new fundamental force, or worse, we're finding that our search in the subatomic realm is as infinite or inscrutable as the search for the end of the universe. What role do dark matter and dark energy play in the subatomic world is not yet clear in its entirety. These two are also on the trail of researchers at CERN, but there have been hints that axions could be the building blocks of dark matter, and these results haven't been confirmed. Have the doors of a dimensional door opened on the LHC? Building the particle accelerator took scientists in Geneva years to complete, and it was also welcomed with approval by the public. But some critics say the experiments underground can be dangerous, and that when scientists here collide particles, the forces here are enormous enough to rip cracks in the fabric of space-time or in the Earth's magnetic field. The Large Hadron Collider is the world's biggest particle accelerator and a marvel of engineering. The facility is the best and, in fact, the only way to explore the world of the smallest particles. Many nations were involved in its construction. Protons, accelerated almost to the speed of light, are fired at each other in a space that's supposed to mirror conditions only a few trillionths of a second after the Big Bang. These are complex devices, capable of detecting and analyzing the debris created in the tiny collisions made by the LHC's ATLAS and CMS detectors. Scientists use huge amounts of energy and the strongest magnets ever made on Earth to speed them along, by increasing the collision rate once again, and increase in energy as well. Even stronger magnetic fields will also be required. As it will deliver even more precise measurements and maybe some new particles or phenomena, scientists expect the upgrade will take this even further. Is it really worth all that effort, and aren't we playing with incalculable risks? LHC critics link strange weather near Geneva to experiments in the LHC. During one of the last test runs of the Big Bird, it's said that a gigantic thunderstorm formed, with the middle of it having something of a strange eye. Like famed medium Edgar Cayce, a boy from America, a self-styled clairvoyant technological genius, came forward. Around the world, Max Laughlin generates amazing predictions. In interviews, Max has said these experiments would have opened a dimensional gate in Geneva as early as 2022, and we would now be in a completely new reality and not remember it. The variety of particles that scientists have now discovered is almost unbelievable. Neutrons and muons, ghost particles, atmosphere messengers. One of the most fascinating, mysterious elementary particles in physics are neutrinos. These are extremely light so that their mass is almost zero and practically interaction-free. In other words, they do not collide with or change ordinary matter, and leave no visible airline behind, neither are they changed in doing so. That's how the neutrino becomes a true ghost particle, or can truly pass through walls, and that's why scientists call the neutrino a ghost. Since those nuclear processes put out these particles in vast quantity, they are used quite a lot. Every square centimeter of the Earth is passed through at least trillions of neutrinos every second, and they aren't limited to the Earth. They occur everywhere in the universe. They are incredibly hard to detect due to their very low interaction rate. Researchers will travel the South Pole to study them there undisturbed. Neutrinos were used by archaeologists to completely illuminate the Great Pyramid of Giza, and thanks to muon tomography discovered a completely new walled chamber inside of this legendary building. The muon is one of those things that is like the electron's heavy cousin, and it's another fascinating particle. When cosmic rays crash into atoms in the upper atmosphere of our planet, muons are created. After only microseconds, muons are extremely unstable, decaying to electrons and neutrinos. Much in the way that muons are anomalies that aren't in line with the standard model of particle physics, so too is the Higgs boson. Specifically, the muon magnetic interaction behavior seems stronger than predicted theoretically. It seems that muons may also lead the way to completely new areas of physics and natural science, say researchers. There are many more exciting videos to come. Press subscribe now.